Now we'll have this result. If A is a map, we consider A as a metric. So such a map A, given any point x in omega, associated with a metric n by n matrix. So AX is a metric n by n matrix. So this map is called a metric valued function. The entries we denoted by alpha IGA. Of course, the alpha IGA are real value function on omega. So we assume that the entries continuous at some point A in omega. Okay. So we have the function. Then the function P, we just mentioned, the function is given by Px is the norm of Ax. So this is continuous. It's also continuous at the point A. Okay. So if the entries of a matrix are all continuous at the point, then the norm of the matrix as a function of x is also continuous at that point. Okay, so this is the content of this lemma. So the proof is not difficult, very easy proof. Firstly, for m by a matrix, we have an inequality we mentioned before, but we have not discussed this. Here the norm, the single bar norm of a matrix is the Euclidean norm. That is the square root of the sum of the square of all the entries. That is I from 1 to m, j from 1 to n, alpha ij square. Where our matrix is A alpha 1 1, alpha 1 n, alpha m1, alpha mn. Okay, so this is our matrix. Then we can consider this matrix as a point in m n dimensional Euclidean space, and then the Euclidean norm is denoted by the single bars. Okay, and this matrix we can also write it in the A1 am. A1 am are the rows of the matrix. Okay, of course this matrix can also be written as A1 an. Here for the rows we use the super index. For the columns, A1 is the first column. So this column is A1, this column is am. Okay, for the column vectors of the matrix we use the lower index. Okay, so this is notation. So using these two expressions, our Euclidean norm of the matrix can also be written as the row vector, the sum of the sum of the square of all the row vectors, the square of the norm of the row vectors, then take a square root. Okay, and also you can also use the column vector. Right? Obviously, this equality are all true. Okay. So now we go to our inequality. Firstly, this part is easier. This part is easy. We prove this part first. The second inequality. For any h in N which norm 1, we consider the AH square. AH square, by the metric computation, AH is a vector. A1, maybe I will use another color. AH is the vector A1H, AMH. Okay? So the norm of the vector AH is the sum of this. Here A1H, because our A1 is row vector, and H we consider as a column vector. So this is the metric multiplication. But if you consider A1 as a column vector, this has no essential difference. Just how to write the vector. You write it in as a column or as a row vector. Okay. If you consider A1 as a column vector, this is precisely the inner product of A1 and H. Okay. So the norm of AH square here is the sum of AI and H inner product and square. Then we apply the Cauchy-Schwarz inequality. The inner product, the absolute value of the inner product will not greater than the multiplication of the norms of the vector. So this will not greater than AI square, H square. But the norm of H is 1. So this is the I equal 1, AI square. So this is precisely the Euclidean norm, the square of the Euclidean norm of our metric A. So this inequality, AH square less than this give us, this means that AH will not greater than the Euclidean norm. But this is true for every H. So our metric norm, that is the maximum for H equal to 1 of AH, of course, will not greater than the Euclidean norm of our metric A. So this proves this inequality here. Okay? This proves the left-hand inequality of this of our claim. Actually, this result is sufficient for our discussion, but the technique to prove the other part of this result, that is this inequality, is also interesting, although we will not need this result later, but because this is interesting, so I will provide a proof here. Next page. So our EJ is the vector 0, 1, 0. The J's coordinate is 1. Other coordinates are 0. That is the standard, the J's standard basis vector of the Euclidean space. So our AJ, what's AJ? AJ is the J column of the metric. The J column of the metric is precisely the multiplication of the metric A with EJ. You see, we know that AJ is AEJ. Okay, so we take the norm, then we take square, This is true. But AEJ, because norm of EJ is 1, therefore the norm of AEJ will not greater than the norm of A. Okay, so this will not greater than the norm of A, then square. So our Euclidean norm of the metric A is so this will not greater than n A square. Okay, so this means that so this is precisely the the first inequality of our conclusion. Okay, so this is the prolongation. Our lemma is to prove the continuity of this function psi. So this inequality we just proved is the prolongation for this purpose. Now we study the continuity of psi. So to prove that psi is continuous at the point A, we need to take a sequence xk in omega. Xk converge to A. We need to prove psi xk converge to psi A. This is the continuity of the function at the point A. But our assumption is that the entries of the matrix, the entries are continuous. Okay, using the continuity of the entries, we have alpha ij xk converge to alpha ij A. Now we applied our inequality A not greater than Euclidean norm to the matrix. Applied A less than A to the matrix. AXK minus AA. What will you get? We obtained absolute value of psi xk minus psi A. This is the absolute value of the norm of AXK minus the norm of AA. Okay, then apply the triangle inequality for metric norm. We just discussed here. This is the triangle inequality for metric norm at the right lower corner of this page. Okay, so we see that this will not greater than AXK minus AA. Okay, this is the triangle inequality for matrix norm. Then using our metric norm inequality, the metric norm and the Euclidean norm of the matrix, we have this inequality. Therefore, this will not greater than the Euclidean norm of AXK minus AA. But the entry of the difference matrix, the entries of AXK minus AA is alpha ijxk minus alpha ija. Okay, so the Euclidean norm of this is precisely the square root of alpha ijxk minus alpha ija square root. Now, by the continuity of alpha ij, we have alpha IGXK converge to alpha IGA. So every this term converges to 0. So the final result converges to 0. So this means C is continuous at A. That's proving our lemma. Okay.